So damped harmonic motion differs from simple harmonic motion in that it accounts for what's called a damping factor or a damping coefficient. So what this represents is, for example, a shock absorber in a car. Yes, it's a spring attached to your wheel, but it's inside some sort of very thick liquid. So it doesn't just vibrate back and forth. There's a substance in there that resists oscillation. So instead of just your car oscillating back and forth forever every time it hits a small bump, there's a sort of liquid in here that absorbs that or damps the motion. So instead of oscillating like that, it's going to oscillate like this. The degree by which you oscillate goes down. And in this formula, notice that this cosine term, that's just going to go up and down forever. It's a cosine, that's what it does. A is just a constant, but this exponential, okay, this is e to a negative number. Now m is just the mass of the oscillating object, it's not changing. B is the damping coefficient, it's not changing. The only thing that changes here is t. So as t goes on, this is actually a negative big number, that's going to 0. So I'm going to erase all these various pen marks. In this expression, a is not changing, cosine is oscillating, but this right here has a horizontal asymptote of 0. So overall, this has a horizontal asymptote of 0. It's oscillating multiplied by something that's shrinking. So the oscillation is being multiplied by this exponential, which is getting smaller and smaller. So overall, it has a horizontal asymptote of 0, although it will cross it many, many times. Okay. So this is damped motion. This is something vibrating, but in a medium that is resisting the motion. Like a shock absorber has this thick fluid that pushes back against oscillating too much. So analyze the graph of the following. This is pretty straightforward. This is really just going to be graph it. Okay, so we graph this function. So the displacement is the product of this damping term, which goes to 0, and this cosine term, which just goes back and forth. So the absolute value, which is how far away we are damped, is given by e to the minus t over pi times the absolute value of cosine. But absolute value of cosine is always less than or equal to 1. Cosine can't be bigger or less than 1 or minus 1. So your displacement is absolutely controlled by this exponential term. Okay. The exponential term, by the way, is always positive, so the absolute value isn't necessary. Remember, a negative sign in the exponent does not make the number negative overall. So as a result, we can conclude your displacement is bounded by this exponential and it's negative, because its absolute value acts as a bound. So if you graph those two exponentials, they are called bounding curves. So basically, if you graph them, here's the positive one, here's the negative one. Oh, my drawing is terrible. Let me try that again. Here's the positive one, here's the negative one. They're mirror images of one another. The cosine, the curve of displacement goes up, and whenever cosine is 1, I actually hit the curve. Then when cosine is minus 1, I'm going to hit this one down here. Then when cosine is 1, I hit this curve, then minus 1, then 1, then minus 1, then 1, then minus 1, and so forth. But these exponential curves that collapse down to 0 act as what are called bounding curves. The motion just goes up and touches 1 and then comes back, etc., etc. Excuse me. The intercepts are where the cosine curve is 0. The bounding curve, the multiplier of e to the minus t over pi, is not going to make it 0, because that exponential term can never be 0. So the only time your displacement is 0 is when the cosine was going to be 0 anyway. So they make a table of a bunch of stuff. The picture is much more illustrative. So in black, we have just the normal cosine curve. These pink curves are our bounding curves. So observe that our actual motion in blue deflects off the bounding curves. So it goes up to 1, comes down to the negative 1, then goes back up to the positive 1, then it's going to deflect off the negative 1, and so forth. Okay, the product of the cosine curve with the bounding curve is our actual deflection. The product of the bounding pink with the cosine black gives us our actual curve, which is blue. So for example, can you graph the sum of two functions? Sure, of course we can. We can graph the component functions, x over 2 and 2 sine x. Now, how would I add them together? We should probably select several values of x where the sine function takes known values and just add them together. So x over 2 is in here. It's pretty easy to compute. 2 sine x, we picked these values because we could easily compute them. Then we can add them together and approximate them to get some points on this graph. And if we plot them, we basically want to join them together with a sine curve, but under the observation that they keep going up and up because we're adding this line 2x. So fundamentally, we do get this sine curve, but it's also following the line 2x. So it's going to go up and down, something like this. So this is a sort of combined motion. The line wants to go up forever. The sine curve wants to oscillate back and forth, so you do both. This is a little bit more relevant to this chapter because we have 2 different trigonometric functions, the sine of x plus the cosine of 2x. Honestly, I don't really want to work through the table. I just want to get right to a computer picture. And it's the pink curve. Okay? So the sine curve has a fairly long period. The cosine curve has a shorter period. But when I add them together, something interesting happens because sometimes both the sine curve and the cosine curve are big at the same time. For example, roughly here. Okay? The blue sine and the black cosine are both positive, so they add to give a pretty big value to the pink function. Sometimes, however, one of the functions is positive and the other is negative, and they'll exactly cancel out. Here the sine curve is at 1 and the cosine curve is at -1. So the 2 waves, the sine and the cosine, have exactly canceled out. They've what's called destructively interfered, whereas the previous example where they were both positive and actually added together, which happens again right here, by the way, is called constructive interference. If you have multiple things that are generating wave motion, they can constructively interfere, which makes the value look bigger. They can destructively interfere, which makes the value look smaller. And if the period of the function is different, here the period is 2 pi, here it's pi, it's going to go back and forth between this constructive and destructive interference in a way that looks a little unpredictable. Okay? But this is basically the combination of a big slow sine curve and a slightly faster sinusoidal curve. You end up with something that looks kind of like that. So that's really all there is to say about it. We're not going to do a lot of complicated work with it. But if I actually just go over to a blank screen, okay, so now I'm going to just sort of extemporaneize about constructive and destructive interference. So how does a speaker make sound? Fundamentally, a speaker is just an object that oscillates back and forth, creating a pressure wave. So if this speaker goes back and forth very quickly, it creates a high frequency wave. If it goes back and forth very slowly, it creates a low frequency wave. If it goes back and forth very far, it creates very high pressures, so that's louder. If it barely goes back and forth, it's not creating high pressures at all. Those are quieter. But how can one oscillating object, a speaker, recreate, for example, a song that has multiple instruments in it? So instrument 1 might be playing a moderate volume thing at this frequency. Instrument 2 might be doing very quiet but very fast frequency. And instrument 3 maybe is doing a very loud, slow frequency bass that goes off and on. Okay, so here's the bass, here's the melody. Okay, it's fairly quiet, but it's high frequency, and here's something in between. Okay, it's a middle frequency and it's at a middle volume. By the time you add all 3 of these waves together, you might get something that looks like this. So fundamentally, we have some fast motion due to our harmony, but it's constructively or destructively interfering with our middle motion. Then the bass cuts out, and fundamentally I'm quieter, and now the bass comes back in. And while I have something that seems to be the same period, there's this long, slow oomping bass that's sort of adding into it. And overall, you now have one, what's called waveform. Okay? This is now one function that represents all 3 things added together. So all you have to do is instruct your speaker to carry an electrical signal that represents this wave, and then it will displace the speaker, positive or negative, according to where this wave is. Then your ear hears a sound pressure wave that looks like this, and your brain can then pick it back apart and determine what were the things that went together to create this sound pressure wave. And a lot of people are like, oh, come on. That sounds ridiculous. Looking at this wave, how would I ever know what individual pieces went into it compared to a live performance where I'm hearing the violin do this and the guitar do that and the singer do that? Well, spoiler alert, how does your ear hear something? Your ear has one membrane that vibrates back and forth attached to hairs that make electrical signals in your brain. Yes, this is a very great drawing. Point being, there's one membrane, okay, that vibrates back and forth. So your ear is already taking multiple sound signals and converting it into a single waveform in your brain. That's just how it works. So a speaker just does the same thing in reverse. It takes a combined waveform and vibrates it back out, so that by the time it comes back into your ears, you're just getting that same waveform, which is what you would have gotten in a live performance anyway. Anyway, so that's something on combining waveforms. There's a whole lot that can be said about this. If you're at all familiar with audio processing, or even image processing, because honestly a lot of it's very similar, you may have come across something called like a fast Fourier transform, or Fourier analysis, or Fourier this. Fourier analysis in math is part of what's called harmonic analysis, which is basically a lot about studying sinusoidal waves and how they interact with one another. And it's a pretty advanced topic. But if you find it interesting, well, you've got to learn a lot of calculus in order to get to studying Fourier analysis. Anyway, that's the end of chapter 5, which is also the end of the course. So thumbs up, congratulations, you're done.